Hello students. In the previous sessions we have just gone through the initial conditions. We have taken different types of problems. We have taken different types of problems and we have found that how to calculate I at 0 plus di by dt at 0 plus, and just a recap of what we did in the previous sessions. We have gone through simple RL circuit. We have taken RL parallel, we have taken RC, we have taken RC parallel. We went through, after this we went through a series RLC series. Then we saw this network where we found I1 and I2 is equal to minus V divided by R1 plus R2 plus R3 as an expression, and we saw this, and this is a case where we have two switching, a SPDT switch where a switch can be thrown to two different positions, and we went through this in the last session. Today we will just see, we will take two more problems and we will go ahead with transient analysis. So, with this knowledge I think it is enough. You can take up any other problem. This, just to recap, we just say R is equal to R, L acts as an open circuit at t equal to 0 plus, capacitor acts as a short circuit at t equal to 0 plus, inductor with initial current acts as a current source, capacitor with initial charge across it acts as a voltage source, and we know the state of these elements at t equal to infinity when there is steady state values. The procedure to be followed, we know that we need to have an history. Switching action takes place at t equal to 0, write the network at t equal to 0 plus, evaluate I at 0 plus or V at 0 plus, write a general expression for di by dt and obtain value for di by dt at t equal to 0 plus, and find the second derivative and obtain. We will just take up two more problems on this and we will go to transient analysis today, and later on we will take up some more problems on RL, RC and RLC on transient analysis to find an expression for the current I of t, where your initial conditions will play a vital role in evaluating the arbitrary constants, as I told you at the beginning of this particular chapter. So, in this particular problem we have two parallel branches, a capacitor and a RL circuit where the switch is closed. Just observe here, what they have asked is to calculate V1 and V2 at t equal to 0 plus, V1 and V2 at t equal to infinity. That means immediately after switching, the value of voltage across the inductor and the value of the voltage across the resistor is what they are interested with, and they want to know what is the value of voltage across the resistor and inductor at t equal to infinity, and the derivative of that voltage dV1 by dt and dV2 by dt at 0 plus, and d squared V2 by dt squared and d squared just d squared V2 by dt squared at t equal to 0 plus is what they know. Anyway, the solution is given here. We will just see how to evaluate all these requirements, because in the earlier cases it was only the current and the derivative of the currents and the second derivatives or the voltage across any switch, what we saw. So, for this we will just go ahead with the problem and we will see how to evaluate the required values. It is a switch where there is a resistor, there is a capacitor, there is an inductor, another resistor in parallel. This is R1, this is C, L, R2. So, the switch is closed at t equal to 0. We can take two loop currents here, I1 and I2. As usual, I can assume I1 is one loop current. It is not specified anything, I can take it as I2. So, first part is the history of the network. We need to see the network at t equal to 0 minus, at t equal to 0 minus. We need to know how the network is. There is no current flow through any of this. The voltage across the capacitor at 0 minus is 0. The current through the inductor at 0 minus is 0. This is what we can write now, easily write, because it is only relaxed circuit, there is no current flowing through this, there is no voltage across this, and the switch is open at t equal to 0 minus. At t equal to 0, the switch is closed. What we should do next? Write the network at t equal to 0 plus. Immediately after closing the switch, the network at t equal to 0 plus. Before this, before writing the network, we need to know what is that he has asked. He wants to know what is V1, what is V2. V1 is the voltage across the inductor. Voltage across the inductor is V1. V2 is the voltage across your resistor. What is voltage across the inductor? Is L di2 by dt. Voltage across the resistor is R2 I2. So, if we want to evaluate V1 and V2 at t equal to 0, right, or a derivative of dV1 by dt, I need to differentiate this equation. If I want dV2 by dt, I need to differentiate this equation and then find the respective values of V1, V2 or dV1 by dt or dV2 by dt. There is a slight change. So, I need to evaluate, to find V1, I need to evaluate di2 by dt, and to evaluate V2, I need to know I2 at 0 plus. So, network at t equal to 0 plus, I will write the network, the switch is closed, R behaves as R, there is no charge across the capacitor, capacitor acts as a short circuit as usual, the inductor acts as an open circuit, R behaves as an R. So, this is R1, this is R2, the loop current I1, the loop current I2. If we just see the voltage across the, what we can conclude from this is voltage across the capacitor at 0 plus is 0, the voltage across this is 0. The current through the inductor or in the loop I2, I2 at 0 plus is 0. There is no current through the inductor because it does not allow any sudden change. The current through the inductor was 0, so it remains as 0 even after switching. So, but I1 at 0 plus is V by R1, V by R1. So, we have this I1 at 0 plus as V by R1. We need to know what is V1 and V2 at t equal to 0 plus. V1 is this, V1 is the voltage across the inductor, V2 is the voltage across the capacitor. V1 at 0 plus and V2 at 0 plus. V1 is nothing but the voltage across the inductor, there is no current flow, there is no voltage drop. So, the voltage across the inductor is nothing but the voltage across the capacitor, right. If you just extrapolate, because it is the parallel branch, there is no current here, no voltage drop. So, V1 at 0 plus will be 0, V2 at 0 plus also will be 0, because there is no current, there will be no voltage drop. This is what is there as a solution even on your PPT. So, we need to know the next one is V1 and V2 at t equal to infinity. We will just take it up later. We will just see what is dV1 by dt from the equations. A, derivative dV1 by dt is L d squared I2 by dt squared, and dV2 by dt is R2 di2 by dt. So, I need to evaluate d squared I2 and di2 by dt. So, to evaluate dV1 by dt, dV2 by dt, I need to know d squared I2 and di2 by dt. A first derivative and second derivative of the current I2 has to be evaluated. So, after writing the network at t equal to 0 plus, we need to write the network, general network after switching. After switching, if you write a general network, it is R, capacitor, inductor, a resistor. This is loop current I1, this is loop current I2, C, L, R2 and R1. Write general integral differential equations for the loops. For loop 1, it will be V equal to R1 I1 plus 1 by C integral I1 minus I2 dt. It is the expression for this particular loop. Coming to the second loop, there is no source, 0 equal to L di2 by dt plus R2 I2 plus 1 by C integral I2 minus I1 dt. So, we have a set of equations, I call it as B. To evaluate di2 by dt, I have an expression here in equation B. If I take this, get an expression for di2 by dt, means di2 by dt equal to, just rearrange the terms, this is nothing but the voltage across the capacitor at t equal to 0 plus. So, it is nothing but minus R2 I2 minus, I can call this as Vc, this is nothing but the voltage across the capacitor. If I say, I can take this at 0 plus later on, 1 by C integral I2 minus I1 is nothing but the voltage across the capacitor divided by L. So, this voltage across the capacitor at t equal to 0 plus is 0. So, if I want to evaluate di2 by dt at t equal to 0 plus, I need to put the conditions at t equal to 0 plus, Vc becomes 0. So, it will be minus R2 I2 at 0 plus by L. It is minus R2 by L into I2 at 0 plus, we have just calculated I2 at 0 plus is also 0. So, di2 by dt at 0 plus is 0. So, this is into 0, I2 is 0. So, di2 by dt at 0 plus is 0. So, your di2 by dt is 0, dv2 by dt at 0 plus will be 0. Therefore, dv2 by dt at 0 plus is R2 into di2 by dt at 0 plus, which is nothing but 0. Therefore, dv2 by dt at 0 plus is 0. Coming to dv1 by dt, I want a second derivative of d squared I2, the current I2. I need to differentiate this equation again. I need to differentiate this again to get the second derivative. Therefore, differentiating the equation, I will get 0 equal to L d squared I2 by dt squared plus R2 di2 by dt plus 1 by C I2 minus I1. If I rearrange to get an expression for d squared I2 by dt squared equal to minus R2 di2 by dt minus 1 by C I2 minus I1 divided by L. I want to get the coefficient of second derivative as 1. So, d squared I2 by dt squared, if you want to evaluate d squared I2 by dt squared at 0 plus, substitute the values of all these things at 0 plus. So, we know that I1 at 0 plus is not 0, it is V by R1, but I2 at 0 plus is 0. So, this term will go to 0, di2 by dt at 0 plus is a 0. So, di2 by dt is 0, this whole term goes to 0. So, d squared I2 by dt squared at 0 plus is minus into minus becomes plus, this term is 0, I2 at 0 plus is 0. So, minus into minus is plus, I1 at 0 plus is V by R1. So, I can write this as 1 by CL into V by R1. So, this is your d squared I2 by dt squared is, I will get this as 1 by C R1 as d squared I2 by dt squared. Now, if you want to evaluate dv1 by dt, it is L into d squared I2 by dt squared. It is, if you want to evaluate dv1 by dt at 0 plus, it is L d squared I2 by dt squared is nothing but 1 by C R1, 1 by C into R1. This will be your dV1 by dt at C equal to 0 plus V by L by C R1 will be your dV1 by dt at t equal to 0 plus. So, this is how you can evaluate V1 at V2 at 0 plus, dV1 by dt and dV2 by dt at t equal to 0 plus. And they have asked us to calculate V1 and V2 at t equal to infinity. So, we need to know, we want to evaluate d squared V2 by dt squared also. So, dV2 is what we obtained, d squared V2 by dt squared, differentiate this again. So, d squared V2 by dt squared is R2 d squared I2 by dt squared. So, R2 into d squared I2 by dt, just substitute the value of d squared I2 by dt squared, I will get it as d squared I2 by dt squared is 1 by CR1. So, just substitute by 1 by CR1, you will get d squared V2 by dt squared. So, with this we have a term, I think L is missing in this case, I2 at 0 plus d squared I2, it is C into L, sorry there is a mistake here, C, it is V by R1, it is C into L, V, this V does not cancel each other, it is V C by L into R1, V C L R1, and then in the same case it is L into dV by dt, I think there is a small correction, L V by L C R1, V by L C R1, L cancels, it will be V by C R1. Finally, if you just substitute here, it is R2 into d squared I2 by dt squared is V by L C R1, V by L C R1. This is an expression for d squared V2 by dt squared. Coming to V1 and V2 at infinity, the questions were to evaluate V1 and V2 at t equal to 0 plus, dV1 by dt and dV2 by dt at t equal to 0 plus, d squared V2 by dt squared at 0 plus has been obtained, and then we want to know what is the condition at t equal to infinity, V1 and V2 at t equal to infinity. If you just take the network at t equal to infinity, at t equal to infinity, this acts as a short, capacitor acts as open, inductor acts as short. These are the final states at t equal to infinity. V1 at infinity, you just say this is the voltage, V1 at infinity is 0, this capacitor acts as open, V2 is this, is nothing but this current, there will be a current flowing through this in this loop, that current will be V divided by R1 plus R2. So, V2 at infinity will be the current into R2, V divided by R1 plus R2 into R2 is V2 at infinity. So, V1 at infinity is 0, V2 at infinity will be V into R2 divided by R1 plus R2. So, we have evaluated all the values what was expected. We just see in this V1 and V2 at t equal to 0 plus was found, which was 0 and 0, V1 and V2 at 0 plus was 0 and 0, V1 and V2 at t equal to infinity was V1 was 0, V2 at t equal to infinity is V into R2 divided by R1 plus R2, and dV1 by dt is V by C R1, it is V by C R1, this L cancels, this L and this L. So, this will be equal to V by C R1 only, what we have obtained, and dV2 by dt at t equal to 0 plus is 0, dV2 by dt at t equal to 0 plus we can just see here it is 0 we obtained, and d squared V2 by dt squared is R V by R1 CL, it is actually this is supposed to be R2, this is R2 into V by L C R1, which has been obtained as it is. So, these are the answers what you got. This is how you need to go ahead with any problem identification. If they ask you to find any other value, you know the relationship. The only difference from the previous problem is he has asked you to calculate V1, V2, d1 by dt, dV2 by dt. Earlier we used to evaluate only I1, di1, d squared I1 and so on. So, now At t equal to infinity, substitute the final values and you will get the voltage across them and voltage across your inductor. There will be only one loop where the current is flowing. If you just extend this problem slightly and see what is the voltage across your capacitor at t equal to infinity. If I just say what is your voltage across the capacitor at infinity, if you just see, which is not asked in the problem, but still out of interest, if you just see what is the voltage across the capacitor, this capacitor voltage will be nothing but the voltage across this. It is same as your V2. We just substitute the numerical values, you will get the voltage across the capacitor. So voltage across the capacitor will be equal to the voltage across the resistor, which is same as V into R2 divided by R1 plus R2. So this capacitor voltage at infinity will be V divided by R1 plus R2 into R2 only, same as the voltage across the resistor R2. So with this, I think we will go to the next problem on the screen. This problem is slightly different. This is how it is different from what we have done in the previous sessions. So in this, they have asked in the network shown, the switch K is opened. See the difference here. The switch K is initially closed. Initial state is switch K is closed. Initially, switch is closed. So switch is closed initially, and it is an opening switch. When the switch is closed, these two becomes redundant. The value of R and C becomes redundant when there is a short. So that is what we need to understand. Switch K is opened at t equal to 0 after the network has attained a steady state with the switch closed. Initially it has been closed, it has attained steady state, and now he is asked you to calculate the expression for the voltage across the switch at t equal to 0 plus. If the parameters are adjusted, there is a slight difference. He has given the numerical values for I at 0 plus and di by dt at t equal to 0 plus as minus 1. If we just directly substitute these values, you will get an expression. He says, what is the value of the derivative of the voltage across the switch dVk by dt? Some different term. He has asked, what is dVk by dt? What is dVk by dt? So we need to write an expression for a voltage across the switch. He has just mentioned Vk is nothing but the voltage across the switch. So we will take up this problem and we will see how to go about with that. I will just write this circuit. It was R1C across the switch. This is Vk, and there is one more resistor R2 and L. Initially at t equal to 0 minus, this is V. At t equal to 0 minus, read the question carefully. In the network shown, switch K is opened at t equal to 0, means because at t equal to 0 minus, switch is closed and steady state has been reached. Long back the switch has been closed. So if I look at the network at t equal to 0 minus, the switch is closed, our inductor acts as a short circuit. It is not at t equal to 0 plus. This is the case of an inductor which has already reached steady state, transients are over, now your inductor is acting as a short circuit. So there will be a current through the loop. So I at 0 minus will be V by R2, if this is R2, because the resistor and capacitor across this becomes redundant. If I have any element across the switch, this is the resistance and the capacitance, becomes redundant because there is a short circuit. So voltage across the switch Vk, you can just write Vk at 0 minus is also 0 because it is nothing but a voltage across a short circuit. So I have a current at 0 minus. So this is nothing but the current through the inductor at 0 minus. Please see the circuit. This current is flowing through the inductor before the switch is open. So, this is a case where the switch is initially closed. Now, at t equal to 0, what happens? There is a movement of the switch. The switch which was closed will now open. It is an opening switch. At t equal to 0, switch is opened. Before the switch, what was the voltage across your capacitor at 0 minus? 0. The capacitor voltage was 0. There is no voltage across the capacitor. Keep this. At t equal to 0, switch is opened. Write the network at t equal to 0 plus. These are the important steps you need to understand. I have a voltage source. Switch is opened. So, your resistance behaves as R. Capacitor acts as a short circuit. There was no voltage, it will not allow any sudden voltage. I have R2, I have R1. My inductor is nothing but a current through the inductor is V by R2. It acts as a current source of value V by R2. Inductor with initial current IL at 0 minus will be IL at 0 plus. It does not allow any sudden change in current. This is nothing but IL at 0 minus will be IL at 0 plus. So, with this we can say what will be the loop current in this, same as V by R2. It is not V by R1 and R2, because there is a current source in this loop, it will not allow any sudden change in current. So, the current through the inductor at 0 plus immediately in this circuit will be V by R2 only. Now, we need to write a general network after switching. So, general network after switching, he says what is the voltage across your switch, plus and minus Vk. Please remember this, Vk, we will just write this here, Vk is equal to the voltage across this combination, voltage across R1 and C. If I take this as current I, it is IL, is nothing but I, same current. It will be R1I plus 1 by C integral I dt. It will be V of k is R1 into I plus 1 by C integral I dt. This is the voltage across your switch, an expression for the voltage across the switch. This is the first part what they have asked. Find the expression for the voltage across the switch, right, at t equal to, the voltage across the switch is, if you want to know what is Vk at 0 plus, is R1 into I. So, R1 multiplied by this current, R1 into the current through this is nothing but V by R2, it is V by R2. This is the voltage across the switch at t equal to 0 plus. The next question what they have asked is, if the parameters are adjusted later on, we will see what is the value of the derivative of the voltage across the switch. What is dVk by dt, derivative of the voltage, dVk by dt is R1 di by dt plus I by C. dVk by dt is nothing but R1 di by dt plus I by C. He has given one important information. I at 0 plus he has taken as 1. He says di by dt at t equal to 0 plus take it as minus 1, right. So, the voltage across, the derivative of the voltage across the switch dVk by dt at 0 plus is R1 di by dt at 0 plus plus I at 0 plus by C. He has given this value, he has given this value. It is nothing but, he says R1 take di by dt. If you just see the problem here, he says di by dt is minus 1, this value. So, di by dt is to be taken as minus 1 plus I at 0 plus is 1. He has asked you to just to substitute them and say it is 1 by C minus R1 is dVk by dt at 0 plus. He says assume the values of the derivative given this side, given di by dt at 0 plus as minus 1, that is amps per second, and I at 0 plus is 1. Okay. So, with this evaluate dVk by dt. This is the question. So, you need to be very careful in understanding the question first and what is the requirement. The question says find the derivative of the switch at t equal to 0 plus. So, we have found the values V divided by R1 plus R2, V divided by into R1 by R2 is the voltage across the switch at t equal to 0 plus, and the derivative of the voltage across the switch. Voltage across the switch is Vk, because this is what is specified in the question. So, Vk is nothing but the voltage across this I into R1 plus 1 by C integral I dt. Voltage across this and the voltage across this is nothing but the voltage, and the derivative of this, just differentiate this, you will get an expression. He has asked you to substitute the values of di and I at 0 plus, substitute those two values and you will get the expression. This is the answer expected. This. So, with these two, I think we have covered quite a lot in transient analysis. I think all these problems will help you in understanding how to evaluate the initial conditions, the derivatives. It can be a voltage, it can be a voltage across the switch, it can be a current through an inductor, first derivative, second derivative, loop currents and all that, and we know in what way these derivatives are going to help us. It helps us in anticipating the form of response. So, this acts as a platform for us to understand the transient analysis. So, we have taken problems on RL, RC, RLC, and we have taken different types of problems. The next part what we have is we need to go through a DC transient RL circuit. The simplest form is the first as an RL circuit. So, normally we start with RL or an RC, whatever. What do we mean by DC transients? First of all, we need to understand, before getting into the subject, the very first slide in the first day, I told you your transient analysis, your initial conditions will help us in evaluating the arbitrary constants. I told you when time comes, I will just tell you in what way it is going to help. So, we have understood how to calculate all your initial values. We will go to DC transients. Before getting into transients, we need to know what transients are. What do we mean by transient analysis? When a circuit is switched from one condition to another, need not be a voltage change. In all the cases, what we have taken is that a switch is either closed, or switch is either opened, or the switches across A and B, initially at A and it is thrown to B, right. So, we have taken any of this. Not only this, if there is any change in the parameters of the network, say for example, if I have a voltage source, okay, we will take a simple circuit so that we will understand a switch with R1, R2 and an inductor. So, by now we will be knowing how the circuit behaves. I have another switch across a resistor. This will be R1, this will be R2, this will be L. Let me assume that this is the switch which is closed at t equal to 0 and this is the switch which will be closed at t equal to 20 milliseconds. Let us take for example that I have another switch which is closed after some time at 20 milliseconds. So, if I just want to plot the expression for current, if we just go back and see the current, or by calculating the initial conditions, we know that the current will be 0 at t equal to 0 minus, switch is open, current is 0, it will not allow any sudden change in current, therefore, it starts at 0 and gradually it increases to a value which is equal to V divided by R1 plus R2. So, the final current before the switch is operated, before this is V divided by R1 plus R2 will be the current. Now, this is time t, 20 milliseconds can be somewhere here. Let us assume that 20 milliseconds is here. Your switching can occur at any instant of time, but when I close the switch at t equal to 20 milliseconds, when I close this switch, this becomes redundant. There will be one more transition and one more steady state. Means the final state, this is the switching action again taking place. There is one more transition. The current finally settles down at V by R1. So, this current will be equal to V divided by R1. What I want to tell you here is, not only the switch is closed or a voltage is applied, removing an element, change in the element, or applying a voltage, removing an voltage, or changing the switch to another position, any changes in the network, there will be a transition, there will be a steady state. There will be a transition, there will be a steady state. Means, what I mean to say transition and steady state is, if I have an expression, this, if I call this as an expression for current with respect to time, this is t, I can just see that there are two, I can split this into two parts. This is your transient part, this is your steady state part. Transient part is the time at which your response keeps changing with time. It can be voltage or current, right. In this case I have just taken current. This is two parts here, one transient, steady state. After switching, one more switching, there is one more transition, one more steady state. So, it keeps occurring whenever there is a change in the network, whether the switch is closed, another element is changed. It can be, I can change R2 itself, I can change the value of R2 to another value. So, there will be one more transition, steady state. So, this is called as a transient part, this is called as a steady state part, right. So, that is what it says. When a circuit is switched from one condition to another, when the circuit is switched from one condition to another, either by a change in the applied voltage or a change in the circuit elements, either way, there is a transitional period during which the branch current and voltage change from their former values to the new values. The current changes from their previous value to the new value, right. It takes time, it depends on the time constant. Okay. The study of this change from initial to final condition or steady state condition is called transient analysis, right. So, actual transient analysis is to see how the current is going to change, what is the time taken for the current to settle down, and so on. Any solution of differential equation. So, anyway, when we write for a simple RL or RC circuit, we get a differential equation. So, solution of differential equation has got two parts. With this in mind, we will just go differential equation solution of differential equation will have two parts called as complementary function plus particle integral, CF and PI. Maths teacher would have told you that it has got two parts, solution of any differential equation. If it is the first, I will come to the order of the equation. So, say for example, I of t, current varying with respect to time, there are two parts of current. One is complementary, the other one is particle integral. This is said to be your transient part, this is your steady state, right. Transient part is the one where the current keeps changing with time, and steady state is the one where the current is constant after switching. So, these two put together is an expression for I of t. Now, complementary function is the one which goes to 0 with time, and steady state remains with whatever the final state of the expression for current. So, with this background, we will just take up RL circuit today, and we will see how to evaluate your current expression for R and L. For an RL circuit, switch procedure is very simple. R and L, I will tell you in what way switch is closed at t equal to 0. I told you there will be an arbitrary constant which comes into your differential equation. Your initial conditions will help you in evaluating the arbitrary constant. So, I will be writing an equation. There will be an arbitrary constant in the expression for or a solution of a differential equation. Your initial conditions will help. What are the initial conditions? Now, I am not going to follow any of the steps, we know them by heart. T equal to 0 minus, I 0 minus is 0. At t equal to 0 plus, I at 0 plus will be 0, right. With this knowledge, we will write a general integral differential equation after switching. V is equal to R into I plus L di by dt. Once you write a general expression, get this to the standard form, means the coefficient of your derivative should be 1, get it to a standard form, means di by dt plus R by L, divide throughout by L, R by L into I equal to V by L. Find the root of this equation, express this as d plus R by L, take out I equal to V by L. What is the root of this equation? Root of the equation, d is equal to minus R by L. So, I have got two parts. Solution means I want to know the expression for current, how the current is going to vary with time. So, current, complementary function of the current, ICF, I told you it has two, IPI. This is your transient part which varies with time. This is your steady state. Steady state current after switching. So, ICF is nothing but I have the root, it is given by an constant A, an arbitrary constant A, e to the power of minus t by tau. T by tau is R by L minus R by L into t, minus R by L into t. It is actually e to the power of t by tau. Tau is minus or L by R minus R by L into t. What is your particular integral? What is the steady state value of the current? Means once the circuit has reached the steady state, all the transients are over, means at t equal to infinity. I mean to say steady state is the network after switching, R behaves as R, inductor acts as a short, so it is V and R. So, it will be V by R, the current through this will be V by R. So, expression for I, current with respect to time, is a combination of ICF and IPI, it is these two put together. So, it is A e to the power of minus R by L into t plus V by R, complementary function and the particular integral. Now, the question is, what is A? How do I evaluate this A? This is what I meant, an arbitrary constant. This is a first order differential equation. First order differential equation will have only one arbitrary constant. It can be k, a, b, whatever you call. This is an arbitrary constant. Your initial conditions will help you in evaluating this arbitrary constant. Otherwise, this is incomplete. So, to find the value of A, I need to know the knowledge of initial condition. So, at t equal to 0 plus, substitute t equal to 0 in this equation. In this equation A, substitute t equal to 0 means I at 0 plus equal to A e to the power, wherever t is there, put t is 0 plus V by R. Now, what is I at 0 plus? I at 0 plus, come back to this, is 0. So, your knowledge of the behavior of the circuit at immediately after switching will help you in evaluating your arbitrary constant A. So, what is I at 0 plus? Is 0 equal to A plus V by R. So, rearranging, A is equal to minus V by R. So, I evaluated the arbitrary constant. If I substitute the arbitrary constant in this equation, I get an expression for current I of t. So, an expression for current I of t equal to A is minus V by R, it is minus V by R e to the power of minus R by L into t plus V by R. I can rearrange this and say, I of t equal to V by R. I just rearrange these two, 1 minus e to the power of minus R by L into t with respect to time. So, I have an expression for current, this is what I am looking at, expression for current in a RL circuit, how the current varies with time. This is the equation what they will be using in a simulation software to find how the current varies with time. Just keep on varying t and plot this on a graph, you will get all the points. If this is t, I got an expression for current, so it will be 0, gradually it increases and reaches a steady state, right. This is V by R, this is t, so it has got two parts. This is your complementary function, this is your particular integral, your steady state value of your current. If you just see here t equal to 0, just substitute t equal to 0 here, this term will become 1, e to the power of 0 is 1, 1 minus 1 is 0, so I at 0, t is 0 means it starts here. If you just substitute for value of t as different times, I will get different currents. So, at t equal to infinity, this becomes 0, this becomes 0, it is only V by R. So, it settles down at V by R. So, that is your particular integral Cf. This is an expression for current I of t for a series RL circuit. So, this is how the knowledge of initial conditions will help us in evaluating arbitrary constant. If it is a second order equation, you will have two arbitrary constants. In such a case, I at 0 plus and the derivative of current di by dt at 0 plus will help you in evaluating two arbitrary constants in a second order differential equation. So, what we have taken today is RL circuit. In the next class we will take up RC and RLC and we will see how to evaluate the arbitrary constants, and we will take some numerical problems. These are general cases what we have taken. So, if you have any doubts, any clarifications on this subject, you can contact me on my mail ID. You can contact me on my mail dineshmn@rvc.edu.in, or just send a message or just call back. Okay.